In this lesson, we'll finish our discussion of big idea number 1, what are redox reactions and how do we describe them, and we'll complete learning target number 2. By the end of this lesson, you should be able to write a balanced chemical equation for a redox reaction using either the half reaction method or the oxidation number method. Balancing equations for redox reactions are sometimes difficult by inspection. 2 methods have been developed to help you. Both methods work for any equation. However, you may find one method easier to use than the other for particular reactions. We'll first discuss the half reaction method. The redox reaction is split into 2 half reactions. These are balanced independently and then recombined to determine the overall balanced chemical equation. This method takes into account the fact that the same number of electrons released in the oxidation are the same number of electrons used in the reduction. Follow the specific steps listed below. Step 1. Write the unbalanced net ionic equation if you're not given it in the question. Split this equation into 2 half reactions. Then balance each half reaction separately using appropriate conditions. Step 4. Determine the lowest common multiple for the electrons and multiply both half reactions by a coefficient to make the number of electrons the lowest common multiple. Then algebraically add the 2 half reactions together. Your electrons should cancel out. And finally, add any spectator ions, if required, in the question. Here's an example. Let's first start by writing the half reaction involving iron. In order to balance this reaction, I need to add 3 electrons on the right-hand side. Because the iron is losing electrons, this is my oxidation half reaction. This also means that my nickel will be reduced. Notice that the electrons produced in my oxidation and the reduction are not the same amount. I have the lowest common multiple of 6. To get 6 electrons, I need to rewrite my oxidation reaction and times it by 2. And my reduction reaction times by 3. Because I'm under neutral conditions, all I need now to do is add these 2 half reactions algebraically together. You notice that my electrons cancel out. Here's the balanced net ionic equation for iron and nickel reacting together. Let's finish the question by identifying what gets oxidized and what gets reduced. This was a fairly simple example because we were under neutral conditions. The toughest and the most amount of work is when you're under basic conditions. Here's an example. Let's start with the nitrogen compounds. On the left side I have a nitrate. On the right side I have an ammonia. I have one nitrogen on each side. In order to balance the oxygens, I need to add 3 waters onto the right. And then 9 H's on the left-hand side in order to balance the hydrogen. These are under basic conditions, so to neutralize the acid, I need to add 9 OH's onto both sides. My hydrogen ions and hydroxides will create 9 waters. However, I have 3 spectating. Let's rewrite this equation so it's a little bit neater. In order to balance this with electrons, we have to check the charges. We have a 1 minus charge net on the left side and a 9 minus on the right side. That means I'm going to need 8 electrons on the left side to balance the charges. Because electrons are being a reactant, this means this will be my reduction half reaction. Let's now do the reaction involving the aluminum compounds. Aluminum gets changed into an AlO2 minus compound. I'll need to add 2 waters onto the left side and 4 H pluses onto the right side. Now, I'll add 4 OH's onto both sides to go to basic conditions. And I'll remove 2 waters that are spectating. In order to balance this reaction, I'll need to add 3 electrons on the product side. This gives me a 4 minus charge on each side. Because electrons are being lost, this is my oxidation reaction. The lowest common multiple between my electrons, 8 and 3, is 24. So I'll need to write my reduction reaction timesing it by 3. In order to get 24 electrons, I'll have to times my oxidation by 8. Now I can algebraically add these together. The electrons are not the only things that cancel out. I have 18 waters as a reactant and 16 waters as a product. Net, that means I've used 2 waters. I have 27 hydroxides as a product and 32 as a reactant. That means net, I've used 5 hydroxides. Let's double check to make sure our final equation is balanced. I have 3 N's on both sides. I have 8 ALs on both sides. For oxygens, 3 times 3 gives me 9, plus 2 more in the water, 11, plus 5 more in the hydroxide, that's 16. On the right side, 8 times 2 gives me 16. And for hydrogens, I have 4 plus 5 more, that gives me 9. And 3 times 3 gives me 9. Charge-wise, I'm also balanced. I have a 3 minus and a 5 minus to give me an 8 minus on the left side, and I have 8 1 minuses on the right side. Pause the video here and try out example B. Restart the video for the answer. Here's the answer for example B. Let's start with the reaction involving the copper. In order to balance this half reaction, I need to add 2 electrons as products. Because electrons are being lost, this is my oxidation half reaction. Now let's do the nitrogen reaction. Nitrate reacts to form nitrogen monoxide gas. Now I need to use acidic conditions to balance this. I have 1 nitrogen on each side. In order to balance the oxygens, I need to add 2 waters as products and 4 H pluses to balance my hydrogens. To balance the charges, I need to add 3 electrons on the left side. That gives me a net charge of 0, both left and right. I have 2 electrons in my oxidation and 3 electrons in my reduction. Therefore, my lowest common multiple is 6. I'm going to take my oxidation half reaction and times it by 3. And my reduction half reaction and times it by 2. Then I can add these half reactions together. My 6 electrons cancel each other out. Nothing else appears too. Let's double check to make sure I'm balanced. I have 3 Cus on both sides, 2 nitrogens. This gives me 6 Os. 2 plus 4 more gives me 6, and 8 H's on both sides. Net charge-wise, I have a 2 minus and an 8 plus, so that will be a 6 plus on the left, and a 3 times 2 plus, that gives me 6 plus on the right.